Yes, sir.
Hello. Okay. I hope everyone present in this class. So today's class again. I want to explain you something about the graph theory only, and then we'll as a briefly, and then we'll discuss to the graph traversal techniques. Okay. So previous class we discussed about what is we entirely discussed about the uh, data structure, what is data structure, and what are the methods of creating our data structure, that is array, linked list, like this we have discussed, and also some of the algorithms for sorting things, that is we have discussed. And also we have discussed about the graph, why we are going for graph, that thing we are discussed. Anyhow, let me recap what we actually why we are going for graph and all. So what is graph? If it's supposed to ask means, if suppose a person is same example I'm just giving to you in the last class. What is example I gave to you is, if suppose I want to trace a person who is forwarded. So from myself to the originator, if it is a single link means I can choose array based data structure for storing the information of myself and then the person who is intermediate between me and originator. But if the originator is sending the message, forwarding his message to certain number of people like this. In this case, what kind of data, if the data I want to store means, I can choose another method, nothing but a tree-based data structure. This kind of data structure is nothing but a non-linear data structure. But this is not a practical case, because I will receive the information from one more person, not only from the single person. I get the information from more than single person. So suppose, for example, if suppose I get the message like that, forwarded message from F node, similarly I get the same forwarded message from C node also. So I want to store the two persons information in my data structure. In this case, the tree based data structure is not possible, because each child, suppose I may act as a child, I will be act as a child for this parent as well as for this parent. But in a basic condition for tree is, the person of child will have only one parent, but parent will have more than two child. So in this scenario, I can't able to choose tree based data structure. So this is what I discussed. That is why we go for a graph-based technology, data structuring. And I give the definition of what is data structure, graph-based data structure. It is a nonlinear data collections. So in this nonlinear data collections, the data can be stored as a node-based information, node-based like that. And it is it will have a more than preceder as well as more number of successor. But in the tree, if I compare the same data structure with nonlinear data structure with the tree means, each node will have single preceder, only one preceder for him, and more number of successor. So that's the major difference between the tree and the graph theory. And the terminologies which are used in a graph is vertex. Another term we call it as a node, and the edges is nothing but the connecting of two vertex, we call it as edges. So the, if suppose I class, if the vertex is labeled means, such a type of graph can be called as a labeled graph. If the vertex is not a labeled means, such a type of graph we call as an unlabeled graph. So in the vertex position, I can choose a person's data or a person's operation, something or addition, subtraction. If suppose I use the same graph theory for expression evaluation means, the operator can be considered as a nodes or vectors, whereas edges can nothing but the way of linking between the two operands. So and similarly, edges can be further classified into two types, that is weighted edges or non-weighted edges. And other terminologies which is in the graph is path and the length of path. Path is nothing but from which node to which node we are traversing, and the length of path is number of edges in the path, we call it as a length of path. And the graph can be we call it as a this kind of graph, whether it's either disconnected graph or a connected graph or a complete graph. If it is a disconnected graph means any one of the node is not having any link with the graph. If the node has at least one path, at least one edge with the graph means, we call it as a connected graph. If each node will have a connected edge, every node in the graph means, we call it as a complete graph. So this is the terminologies we have defined, and this is the example I'm just showing you. These are this encircled information A, B, C. We call it as a vertex or node, and the link which I'm connecting between A and B, we call it as a edge here. So this is one edge, and this is one edge, and this is one edge. And before that, let me ask you one more question. Is this visible to everyone? What I'm currently showing?
Yes, sir.
Yes, sir.
Okay, fine.
Yes, sir.
So if the, since the connecting line has no direction, so we call this kind of edges we call as a undirected graph, as well as edges not having any value, we call it as a unweighted graph. So since the edge is not direction, we call it as an undirected graph, and it is not having any weight. So the adjacent vector of vertex A we call as vertex B and vertex C. Adjacent vectors. Who are the adjacent vectors of B means? Next, the connecting node of B is A and C. Similarly, for node C, A and B are the adjacent vectors. So adjacent vectors means the neighboring vectors we call as an adjacent vector. Immediate neighboring vector we call as an adjacent vector. So compared to the previous graph, this has some smaller difference. Here the edge is having some directionality, so that kind of graph we call as a directed graph. Here the adjacent should be called based on the source. Suppose if who are the adjacent node for vertex A, if I asked, means it is the point giving the information or data to the vertex B and C. So the A vertex adjacent vectors of A are B and C, whereas adjacent vector for B is only C, because B is giving information or data only to C, not to A. So the adjacent vector for B is C. Whereas when I consider for vertex C, who are the adjacent vector, means it is not giving any information or data to neighboring nodes, that hence it has no adjacent vector. So this is a major difference. So for vertex A, B and C. For vertex B is only C. For vertex C, there is no adjacent vector because it is not giving any information to anybody. And the graph types, if I asked, means there are two types, that is labeled or unlabeled. And if it is labeled, means it can be further classified into weighted or non-weighted. This weighted and non-weighted it is classified based on the edge value. If edge is having any value, means we call as a weighted graph. If edge is nothing, it doesn't have any value, means but default value is considered to be 1. So we call it as such a default value 1 weighted graph we call it as a unweighted graph. Similarly, if I give the same weighted or unweighted edges in a directed graph, means we call it as a directed unweighted graph or directed weighted graph. See, these are the types of graph, and this is what we are discussing in the last class also. So labeled means unlabeled. This is unlabeled because the node is there are 1, 2, 3, 4, and 5 nodes are there. All the nodes having no label at all. It is not pointed by any name. So we call it as an unlabeled graph. And also the edges is not direction, so we call it as an undirected graph. And also now it doesn't have any weight, so we simply called as undirected, unweighted, unlabeled graph. We call this kind of graph is like this only. Suppose here I am calling, if I suppose to ask, now tell me what kind of graph it is, means it is unlabeled, undirected graph. Okay, and if I suppose to ask what kind of graph it is, means here the edges are labeled and it is also directed. We call it as a labeled directed graph. Got it. These are the questions I discussed in the last class, and these are the sample example of how actually the graph looks like. If it is unweighted undirected graph, the graph will be look like this. And if it is unweighted, if it is a weighted directed graph, means the graph looks like this. Here the weight of which edge for the A to E is 10. And similarly for a weight of wedge, the weight value, that is this weight value we call it as we can refer like the distance between the two nodes. For example, if the same graph theory, if I'm plotting for the networking sector, if suppose we are doing like this, means we call this vertex A as one computer system, vertex B as another computer system. These two systems are one-to-one connected, and the distance between the two systems we call as a weight value of 10, means it may be equal to that of the 10-kilometer distance. It is separated by 10 kilometer like this, and it is separated by 2 kilometer like this. Similarly, C and D vertex is separated by 10 kilometers like this. We can call as a weight value. So weighted means nothing but maybe a distance or a combustion or traffic level or a power consumption or bit of some kind of terminologies we are so far doing in a regular practices. So in such a way we can interpret it, or we can interlink like that. Okay, well, fine. Then simple directed graph is like this. And how do we represent the graph? So it can be do by two. It can be represented by two ways. One is adjacent matrix. Another one is adjacent list. So what is the difference between? We can choose whichever you like, which is convenient to you. Both are the same operation only. So for here here it is not a weighted. So default weight value is 1. So how many vertex are there means vertex A, vertex B, vertex C and D. So I represent that vertex A, B, C and D in a row wise, sorry, in a column wise as well as in a row wise. And what are the edges between vertex A to vertex A is obviously there is no self referral. So I will put self node equal to that of weight value as 0. Okay, by basically the self value is 0. So when I compare A and A 0, B and B, the vertex is 0, the weight value is 0. Vertex C and vertex C, the weight value is 0. Like this, the diagonal element will be 0. Whereas vertex, when I comparing the vertex A to vertex A is connected to what are the nodes? If I cast it means the vertex A is connected having the edge with B, having the edge to C, having the edge to D without any weight. So we make it as vertex A to B is 1, vertex A to C is 1, vertex A to D is also 1. Similarly, for vertex B, it is having connection with vertex A and as well as vertex C. So I call as a vertex B to A is 1, vertex B to C is 1. But vertex B to B is always obviously 0. Vertex B to D, there is no links here, there is no edge between B and D. We can make it as we can assign the value as 0. So like this, I'm keep on doing I can represent the graph in the form of matrix. If I represent the adjacent edges of each vertex in the graph in the form of matrix means we call such a represent as adjacent matrix. If similarly for the directed graph, here vertex A is for the vertex A, adjacent vertex are. Can anyone find it out? What are the adjacent vector for the directed graph? How do you find the adjacent vector for the directed graph? For vertex A, which are the directed adjacent vectors?
B, C, and D.
B, C, and D. Because A is giving information to B, A is given information to C, A is given information to D. So B, C, and D are act as an adjacent node for or adjacent vertex for vertex A. So here I put for A 1 and 1 and 1 to B, C, D. Whereas for B, it is giving information only to C. So for C only I'm putting as 1. See, for C only I'm putting as 1. Whereas for D, it is not giving any information to anybody. So for the D row is entirely 0. Similarly for C also, it is not giving information to anybody. It is taking information from the other node. So I'll put the value as 0. So this is a way I'm representing the graph in the form of matrix based. So this is the one way of representing your graph. Similarly, I can represent the same graph. This is another example for this. If I put some value, weight value means for the weighted graph, if I put means instead of substituting value as 1, I substitute a corresponding weight value. So for A to B, the corresponding weight value is 21, so I substitute as 21. For A to C is 12, so I put as 12. For A to D, the weight value is 31, I substitute as 31. Similarly for all the cases also. So this is another way of the same matrix representation for graph. And another way of representing the same graph, which first in the beginning level I'm just discussed. So here again I'm giving example of undirected graph. Here there are, as usual, we have 4 vertex. So I represent 4 vertex in a row ways, and here I'm substituting the adjacency like this: B comma 1 comma colon C comma 1 colon D comma 1, because for vertex A, B, C, D are the adjacency and its weight value is 1 and 1 because it's unlabeled. So I represent adjacency in the form of tuple. When I compare the same thing in Python programming, this kind of representation acts as a tuple, and this is another tuple, this is another tuple. All the tuples are put into the list. You can I can simply put a square bracket here. Why I'm why I'm putting all these tupled information, that is separated first edge, second edge, and third edges, I'm putting in a form of list. If I asked means a simple question. Suppose this is a vertex A having link with vertex D. If suppose there is currently I have an edge between A to D. Okay, If suppose the networking between that is the connection between the node A to D is getting disturbed by some kind of natural problem or some kind of artificial problem, some people make some kind of damages to the link, what will happen, the information from A or data from the A is not going to D because if the connection is disconnected. In such a case, what are the adjacency to A means I can put B and C only. I can remove this tuple B comma 1 tupled information can be removed entirely. So this collection, this kind of adding or removing by adaptively, if I want to do means I put the adjacency list in the form of list only. But each element can be substituted in the form of tuple B comma 1 because its weight is until I have edge, the default weight value is 1 only. There will be no change at all. So I will put in the form of tuple. Are you clear with this case, everyone? I'm representing the same vertex in the form of list. Is it okay?
Yes, sir.
Hello. Fine. Anybody put any questions?
Okay, sir.
Fine. Thank you. Let me continue this class session. Okay. So this is a way of representing. So for this case, I just like to show how to represent the same graph theory in the form of computer programming. So this is what so far discussed. This is a nonlinear adjacency type of we can represent it, and these are the types of graphs and how to define the what is the path of graph for either text A to E means I can flow in this direction. So if A to E path is I can go this path A to C, C to D, D to E is one path, A to B, B to D, and D to E is another path. I can choose two paths, and the length of two paths is nothing but number of edges between the two paths we call as a length of path. So these are the things. Now come back to the topic of how do we represent the same matrix in the form of graph. So let us assume this graph. So here this is the graph. The vertex A, B, C, and D are four graphs. Four nodes are there, and A to B is connected, and B to C is connected. D like this it is connected. I represent the same graph in the form of matrix. If suppose the same, this can be written by handwritten paper, but how the computer can able to understand this is a graph, how the terminology, the same terms, how do I represent in a computer term means I can represent with a variable called graph. This is a graph I'm just putting in a variable. I put in the form of dictionary. A dictionary consists of vertex A is nothing but this is a vertex, this is a row 1, right? So row A is A, and it consists of only one edges. So I represent in the form of list. Similarly, I can put in another form also, like this also, as like in a given program, I can write like this also, B comma 1, like this I can represent if I want to clearly represent means. But for simple cases, I represent like this, just for our simple understand in a computer terminology. So for vertex A, it is connected to B. For vertex B, the list of adjacency are vertex B, which are the adjacency A, C, and D, right? So I represent A, C. Okay, but some people will write in another form also, A, D, C. I can write like this also. It is your wish only. But how will it affect something like I can represent like this also. There is no problem at all. For the vertex B, adjacency of vertex B are A, D, and C. I can write, but is that creating any problem means surely it will create a problem while you are doing traversal. I will show the same example in following such things. So this is where you represent the same adjacency list in the programming concept. So when I execute it, it will show vertex A has adjacency of B. For the vertex B, the adjacency nodes or adjacency lists are like this. For vertex C, these are the adjacency list. For vertex D, these are the adjacency list. So this is what I want to represent in a computer-based operations. Okay, welcome back to the topic. So this is what we are discussing in the last class also. Well, now simple question so far. What is the path to, what do you choose a path if I want to move from A to E? Same question I asked, right?
A to B, B to D, D to E.
ACD.
Yeah, there are two different paths currently for the same exam. I'm just giving. No worry about it. So these are the two way. So what is the path length means? If suppose you choose this is a path A to C, A to C to D, and D to E means I can choose how many edges means A to C is one edge, and for C from C to D is another one edge, from D to E is another one edge. So totally three number of edges. So these are the path length. Similarly for here also three number of path lengths is available. Okay, fine. So next quiz to you. Can just take a piece of paper and just try to represent the same graph. Is it visible to you guys? The graph is visible or not?
Yes,
Clearly
sir.
visible.
Yes, sir.
If this is a, they have some part of information is hidden. Here is a E node. Consider this is a E node. Here I'm showing, right. This is a E node. So if you can you able to represent the same same graph in the form of adjacency list. The question is, I mean, it is not a matrix. Try to represent the same graph using adjacency list based representation. Have you completed or went for paper taking? I'll tell what is the adjacency list for vertex B. Just type in a chat window. Just type in a chat window.
C, 1, D, 1.
Okay. Oh, C comma 1 and D comma 1. So I hope if you did like this, it will be well and good. So no problem. If for this case, what is the adjacency vertex for adjacency list for vertex B? Same vertex B. The same graph, but here it is not directed.
A, 1, C, 1, D, 1.
A comma 1, C comma 1 and D comma 1 are the adjacency list. I hope if you did the same thing means it's okay, well and good. So this way represent the graph. Now we go to the way of traversing the graph. If suppose, what do you mean by traversal means how do you move from the particular node that will cover the entire nodes in the particular data structure. If suppose I choose a tree, from which point I will start to travel. If the data structure is tree based data structure, from which point I will start to traversal. What are the terms are there in a tree? You can represent nodes in some, right? What are the nodes are? How do you represent the nodes in the tree based data structure? Well, in the tree-based data structure, we represent the starting node as a root node. Then from the root node, we call as a successive nodes or successor node. At the last node, we call as a last level of node, we call as a leaf node. Like this, we are going to represent, right? So if I want to traversal in a tree-based data structure means I will start from the initial position. That initial position is nothing but my root node. In the tree, we have only one node. That one node we call as a root node. But here we don't have anything called an initial node. We can start traversal from any point of vertexes. So in the graph traversal, is not similar to that of tree based. So if somebody start to traversal from C, he will get some kind of root mapping. If suppose a person start to traversal from E node, he will get some kind of root map. So this root mapping in a graph base is totally different from the tree based data structure. Well, so let me have some condition how to make traversal in a graph. So before this, let me tell you what is the purpose of traversal. With the help of graph traversal, we can do some kind of operations such as I can insert some elements in or remove the elements in the graph. I can find the shortest path in the graph. I can also find the element if there is a present or that, and also I will traversal what are the items are there in a graph. This is the way of things we can do in a graph based traversal. And what are the vertex means from where, what is the algorithm for traversal means first I want to start from particular node. That particular node we call it as a start vertex or start node. Then from that particular node I start to define its own adjacency list. From that adjacency list I start to further traversal, like it has to traversal in a straightforward manner till I reach the entire graph, till I have dead end condition. Until then I will keep on traversal. If there is, if I suppose I'm moving, for example, this is a, let me go, suppose I start traversal from here. This as I will, if I start from here, a node means I consider this as a start vertex. From this I will go only to B and C because I have no idea about vertex D and E, because I have only one thing, that is nothing but A has, sorry, I have A has the adjacency to vertex E, vertex B, and vertex C. So I will go to either any one of the nodes I start for the traversal. This traversal will continue until I reach the until I have no further more traversal. This is the way of, let me explain you in a clear manner with the help of the presentation. Okay. For this crash traversal, I can choose two ways. One is breadth first search and another is the depth first search. Breadth first search is similar to that of levels traversal in a tree organization. Level traversal means level order in the tree. We can do 3 or 4 different type of traversal. One is pre-order traversal, post-order traversal, in-order traversal. Similarly, level order traversal we are discussed in a topic of chapter 4, right? So do you remember? I hope you have some kind of idea about what are the types of traversal in that. In that one type of traversal is nothing but level order traversal. So the same level order traversal is using in here we call it as a breadth level traversal. If suppose I'm traversal in a particular node, we call it as a depth level traversal. We'll discuss with the help of example. Okay. So let us consider this is a graph. This is a directed graph. So in the depth first traversal, how do I'm going to start traversal means just simple. Let me assume that I want to make the start node as vertex A. It is not a condition that I want to start only from vertex A. Based on the question only I can make it chosen. So if suppose I ask to start traversal depth first search from vertex B, means I have to start from B as a start vertex. So anyhow, let me start with the vertex A. So if suppose I choose a vertex A for depth first search, means for vertex A, what are the adjacency means B, C, and D. But if in the B, C, D list, I will suppose in the list I will consider B as a first list element, means I am further going into the adjacency of B. So what is the adjacency of vertex B means currently B as a current vertex. From B I am start to further traversal. So it will go to E. From A I will go to B. From B I will go to E. From E there is no further traversal. So I will stop traversal. I will come back to the previous edge, previous node. So previous node is B. So for this B, is there having any other adjacency vertex means? Yes, it is obviously having adjacency vertex because B has two adjacency, E and F. No, so already E is visited and F is not visited. So I will go to F node. From this F node, is there any other vertexes to further traversal means? For the F, it has two adjacency, that is C and H. So I can choose either H or C. Suppose I put the H is starting first point means I will further traversal to H. Then from H, is there any other traversal means? Yeah, it has a link to vertex E. It has a link to vertex G. But vertex E is already visited, so I will not go to the E vertex. So instead of going to E vertex, I will choose the alternative path, nothing but G vertex. So it goes to vertex G. From G, is there any other adjacency means? It is not having any adjacency because it is act as a source. So obviously there is no further traversal. So the system will go back to H2. It is from here. It is called from GH. From H it is called from F. So from F it is it has pointed only one point, that is H point. It is not pointed C node, right? So it goes to C node. From C node it goes to D node. in this way of traversal we call as a depth first stretch. So depth first means which node I'm choosing. I consider that particular node as a visited node. From the visited node, I will go in a particular orientation. I'm narrowed down to this certain vertexes or certain nodes until there is no further adjacency node. If suppose I'm from here B, I'm going to E means this E should not have any adjacency. Until then, I will keep going deep and deep and deep. If suppose I'm going in deep and deep until I complete to the last most leaf leaf node means this kind of traversal we call as a depth first traversal. Are you okay with this concept? What is the difference between what is the meaning of depth first traversal? Yes or no? Okay, fine. Let me anyhow try. We will again come with a question of using depth first in a later session. Now let me discuss with the breadth first, the same graph. If suppose I want to do same traversal from vertex A, but I'm traversal in the form of in the algorithm called breadth first level, breadth first traversal. Here it is. It is similarly looked at of level search, level order traversal in a tree way. So it is adjacency. It first complete its adjacency, then it goes to level by level. It is keep on going. So from A, it goes to it will visit B, C, and D. In a queue-based operation, it will visit B, then C, and then D. After visiting B, C, D, it will again visit to its adjacency. From B, who are the adjacency means E and F. So it will visit E and F. Now it is not further goes to from it is not going further to from E's adjacency or F adjacency. It will go to this not goes to E and F. It will go to C a point because it is not completed. So it's checked for whether it's having any adjacency. But C has no further adjacency, so it goes to D node. It will check for any adjacency. But I will come back to the previous node and whether is there any other adjacency. But here F has no adjacency. So the further I go back to the H, whether H has any adjacency. Obviously H has adjacency to F as well as for G. So already F is visited. So I will go to G node. From G node, is there any other adjacency? Means yes, D is adjacency. Since D is not visited previously, I'll go to D. From D, is there any other adjacency? Means yes, it has adjacency to A, but A is already visited, so the traversal is stopped. This kind of traversal we call as a breadth first traversal. The same example, but for directed graph, it is totally different compared to the undirected graph. But the logic is same logic only. I will choose only the unvisited vertex and also the adjacency vertex. This is the only one condition to traversal. Is it okay? Are you okay? Or you want to demonstrate again? Same graph from A I'm starting. It is goes to B. From B if suppose to traversal, it goes to E. From E it goes to H. From H to I can travel either F or G. If suppose I choose F, I will check for its adjacency. For F, it has C as adjacency as well as B as adjacency, but B is already visited, so I will choose vertex C. From C is its adjacency are A and H, A and F, but A is visited already, and also F is also visited. So I will stop traversal and come back, return back to the topic of H. From H has other adjacency called G. It goes to it goes to its adjacency called D. From D it goes to A, but A is already visited, so the traversal is stopped. H. So same breadth first traversal for the same undirected graph. From A it travels to B, C, and D. From B, C, and D it travels to E, F, and G. From then it will traversal to H. But previously the traversal the previous directed graph, the traversal come from F to H. But here it comes if the computations compute from the starting point. Here the in this level the starting point of no vertex is E only. So it's whether E has any adjacency means E has adjacency to H. So it goes from E to F. Previously F to H only I am given in a directed graph, but in undirected graph which is at having adjacency, you will choose automatically. And from when I come to the F, it has no further adjacency because H is already visited, B and C is already visited, so the traversal is completed. This is a type of breadth first traversal. Are you okay? Is there any question based on depth first traversal or breadth first traversal? Shall I go to the next question? Okay, the question to you guys. So you take the paper, start do traversal, depth first traversal from the vertex B. What are the terms we will get? The answer, just type the answer like this. Previously I write like this. No, is it visible, guys? A, B, C, D, E, F, G, H. Is it visible clearly? Is it visible, guys?
Yes, sir.
Entirely it is visible to you guys? Here, A, can you able to visualize these things? The highlighted information. Yes or no?
Yes, sir.
Now try to write the same kind of list for this DFT from vertex B.
Already sent.
Oh, is your answer? Pradeep, 166. Fine, let me check. If I start from B, I'll go to either A or E or F. Suppose I put A as an initial list, means I'll go to the E is the next list. From A, I can go to either B or C or D, but B is already visited, so I can't go to C only, not to B or else D. So from C, I can further traversal to either F or B, sorry, either F or A, but A is already visited, F is not visited, so I'll go to from C to F. From F, I can go to B, C, and H, but B and C is already visited, so I'll go to H. From H, I can either go to E or G or F. Since F is already visited and also E and G is not visited, I can choose either E part or G part. If I choose, if in my list, if I put E as a primitive value and G is a secondary value, means I go to E only, and then only I will go to G. From G I will go to D. From D I can't able to go further because A is already visited. So this the answer is A C B A C E H E G D. But some people get some other answer also. No worry about it. I will tell you what is actually what kind of answer will be. So for this case, let me give the same thing with the help of exam with the help of program. So for this, I will create one class. For this class, I'm using one inbuilt function called a default dictionary function. This default dictionary function, the purpose of default dictionary function is it will create a dictionary type. In that dictionary type, I will pass the values and the form of in the type of list. So I can create such a fashion. Here the graph is a variable which it holds the collections like previously holds something, right? This is a variable I'm using, right? Here it looks like graph dictionary based list, right? The keys are a string, that is nodes, and it is for keys values are in the form of list. If I want to make such a kind of thing only, I'm for this purpose only I use this kind of default dictionary, empty default dictionary. This is the purpose. And then for breadth first depth first search, I using one set function. In that set function I keep on including the visited information. Similarly for breadth first visited node will is a list type, it will keep on putting the visited information for if I traversal with the help of BFS. And I'm adding the edge by putting this kind of thing. I'm putting the source and also target. It will establish the source to destination. So how it looks like means the since graph, the variable graph is a dictionary. The graph dictionary, if I put like this, if since g of here is a graph is a dictionary, right? The graph is a dictionary. If I want to append the edge means like this grabh for vertex a. Already, for example, here the vertex A is having the edge with B, so I will pass. Already B is a vertex, no. So if I want to append in the list, I want to append the another edge. That edge is A as having edge with suppose C means. Okay, so now the vertex A is having B is a previously it has a B only as a edge. Now it has C also. B and C also. Let me print here. So previously it has only B as a edge, A as edge with B only, and whereas A now A has appended with one more edge, that this edge is connected to C node. So I will append that C information. Now it becomes A becomes its edges its adjacency are B and C. So for this case only, I am defining the definition graph dot source from where I want to append and to what I want to append. It establishes the edges. And the depth first search algorithm, I will check whether the node is visited or not. If it is not visited, I will just append that particular node in my visited information. And if it is not visited means what I will do means I will check for its neighbor. The dictionary will give its neighbor. Until the neighbor is completed, it is keep on visiting itself. This is a this function is nothing but a recursive based functioning, list inside list, I mean function inside functioning calling. Based on this depth first algorithm will execute properly. Similarly, breadth first algorithm is nothing. Breadth first means level based operation. So for this case I will just put the visited node as I will put the visited node in the particular variable appended. After that, what I am doing, I'm that particular visit node will be put into the queue. Until the queue is empty, I'll keep on visiting its neighbor. This is similar to that of what is the operation I was discussed in the demonstration, right? The same operation I represent in the form of graph programming. So you'll execute it. I will show you how actually it is executing. I'll share this code. You just run the same code as well as upon some kind of operations, and you just develop yourself. Okay, now the same. Let me write with this particular graph. My graph is equal to. Let's come back to the topic. Okay. Now let me talk with the help of the same example. Here A is connected to B, C, and D. So I want to make A is connected to B, A is connected to C, A is connected to D. So the list will becomes like A of B, comma C, comma D. So the first primitive element is B, its next element is C, next element is D. If suppose I disorder the same thing, if suppose I add the first edge is A to B, then A to D, then A to C means the element is totally the meeting point is keep on. I mean it is varied. So you just check that the same example. This is the same example I'm just drawn. Then from B it has edges with E and F. So B to E, B to F is edges are added. From D it has only edge to G. So from D to G, then from F it has C and H. I can write H comma C also, but since for the higher ordered purpose, I write F to C, F to G I added. Then from F to C, F to H, sorry, F to G is not there. So let me uncomment it. Let me comment. F to G is not, there is no link. So I'll uncomment it. So F to C and F to H. From H, it has a connection to E and G. So from H, it has connection to E, from H to G. So now the graph looks like this. A's adjacency are BC, D. This what kind of thing it is looks, what kind of representation it is? Graph representation. There are two representations, right? One is adjacency matrix, another is adjacency list. Now tell me what kind of representation is looks like.
Adjacency list.
Yes, adjacency list. So A is to B, these are the nodes I'm just represent. So if I do by breadth first search and depth first search, if I do breadth first search, it first I'm starting from, let us assume that I'm going to start from A. From A node I'm going to start. So from A to which it is going to traversal. From A I'm just let me go back to the topic again. From A it goes to B, right? From A it goes to B. From B it goes to E, right? From E it goes to E. From then it goes to F, E to E. Then after E it goes to F. After F it goes to H. After okay, after this it goes to C. Some kind of mistake I made it. Here it is. Oh, from F it has C and H, right? I'm sorry. From H it has C and H, right? So from in this case F for the vertex of F, H is not an immediate element. C is the first immediate element. That is why it goes to C. Okay, the same problem I'll showcase you. If suppose I write like this, H comma C. Now it changes, right? Now it looks like the same program like this. If the list adding edge list adjacency ordering is varied, means the variation is also occur. So this traversal is mainly depends on how you create, how do you represent adjacency list, as well as how do you demonstrate it DFT also. So in this previous example, if I add C, first H then C, means it looks like this. From F to H only. From F it goes to H only. From H it goes to G only, like this. From G it goes to C and D. C and D, like this only it will represent. But actual scenario is not like that. I can write in this ordered manner, means it goes in another fashion. Okay, anyhow, you just try to work with yourself. Similarly, for breadth first traversal, it first go to ABC and then DEF and GH. So it goes to A and then BCD, then EF and G, then finally it goes to H. This is for directed graph. Now let me come to the undirected graph. For undirected graph, how do you represent the edges? Means simply like this. From A to B, if I raw, means from B to A, I have to add the edges, because it is it is having bidirection. Undirected means it has connection. There is no only one direction. From A to B as well as B to A has a connection. So I have an edge like this: A to B, B to A. Then from A to C, if I add edge, means from C to A also I add to edge. A to C, if I add, means similarly I have to add C to A also. If I add A to D as one edge, means A to D edges I added, means D to A also I have to add an edge. I think I added. Let me get where I actually added. Okay, let me add G comma edge. Similarly, from B to F, F to B, F to B, B to F, E to E, like this the edges are added. So if I do the same traversal, it looks like this: A to B, B to E, E to H, H to F, like this. A to B, B to E, E to H, and then H to F, E to H, H to C, it's F to C, then F to C, then C to G, C to G, then G to D, G to D. This is the depth first search for undirected graph. Similarly, for the breadth first search for undirected graph, A, B, C, D, E, F, G, then H. A, B, C, D, E, F, G, and H. Right? So this is the example. Now I will just talk with our question which I asked. So if suppose I draw like this, if I want to start traversal, I want to do some traversal from B vertex. So what are the adjacency? If I do by BFS, means I will start search like this. BFF from which node I want to traversal. So I hope we will get this kind of answer. From B to A, and then from B to A, then A to C, C to F, B to A to C, C to, oh, it is undirected. This is the directed graph, so let me draw it. From B to E, oh, it is undirected. Sorry. Yeah. So from B to A, A to C, here also A to C, from C to F, C to F it is traversal, from F to H, H it is traversal, from H to E, then S to E, then G to E to G. After E it will go to G. After G it goes to D. After G it goes to D. Got it? If I do the same example with a breadth first search algorithm, now I'm doing the same example for the directed graph. A to B. Now you tell me, if I do traversal from B for the directed graph, what will be the result? It starts from B. From B, it will point to E and F. It goes to E, and then it goes to F, and then it will just tell me the answer, and we will quit this session. For this graph. I hope we will get this like this. From B, I'm starting. Its adjacency are E and F, so I'll go to E. I visit the E right now. From E, there will be no further traversal, so I'll go back to B, and from B, where it is a traversal means from B to I can go to F. From F, I will have edge to either F or C, so H or C. So I'll go to C as in the list forwarded, and then from C it is not going further depth, so I'll go to H. From H I will travel to either E or F, but E is already traveled or visited, so I'll go to G. From G, is there any further travel means it is not travel, so I'll go back and back and back until I try to find whether any other adjacency is left, but unfortunately no other adjacencies are left. But obviously I can't from B. If I start at traversal means in the depth first stage, I can't able to go to D, A and D. This is the scenario. So let me check with the example also. Now I'm just doing the same example. I'm from the same program. Same directed graph. I'm just traveling with the depth first search. In this case, B to E is traveled. B to E is traveled from B to E. Then from B to E, after B to E, it goes to F. It goes to F. After F, it goes to C. After F, it goes to C. It goes to C. After C, it goes to H. After C, it goes to H. After H, it goes to G. After H, it goes to G. The same so this is the answer for depth first search if I start my vertex from B. Right. Similarly, if I do the same example, try to find the same, do the same problem with the graph starting from vertex F. And now tell me what are the vertex you will get. This is a simple answer for you. If I do with the breadth first search as well as depth first search, tell me the trace path of the graph if I start from vertex F for both the traversal method, DFT or BFT. You'll get the answer like this. Same answer. Okay. So this is a session. The session is completed. I hope this session will be useful for you. And next we will discuss about the spanning tree and topological sort. The next coming classes. I hope this section will be suitable. I mean, is there any doubt with you? Are you clear with the topics? I've shown the answer to you. You just go through it. I'll give the same sample of code to you on the web page or to your mail ID, and also for the C section also I will send through Vivin sir. You just go through the code as well as you execute the same code or alter the coding level. I'll create your own way of representing your graph. You draw your graph by manually in a paper. With the help of that paper graph, you do the same traversal from any vertex. You just do some vertex for practice purpose, and then try the same example using the same in a example program also, and tell me whether just congratulate yourself if you did properly and correctly. Any questions? Fine.